kind of take you through the big picture on what we started on Friday. And don't hand that sheet in yet. We need it to transition into what we're going to do today. So, if you look at like number 5, okay? And let's say that you just wanted to get a rough idea of what's going to happen on number 5. Let's just say we're going to make a sketch, okay? Let's just say we're going to make a sketch. So, if you're going to do this tit to tail, okay? So, the first thing you're going to do is you're going to draw vector A, 5 centimeters at 0 degrees. So, here's vector A. Then you have vector B. Now, vector B is pointing up like this, however many centimeters at 90 degrees. This is 3 centimeters doesn't mean anything. Okay? So, here's going to be vector B. So, you're going to take vector B and you're going to draw that from the end of vector A. So, you're going to come up like this. Here's going to be vector B. From the end of this, you're going to draw vector C, which is like 4 centimeters at 120. Okay? So, again, you're going to measure here. This becomes a whole new X and Y coordinate system. You're going to measure around 120 degrees, and you're going to have that vector. Now, where do you draw the resultant? Origin out. Okay? So you're going to come in here, and you're going to draw this vector. You're going to label it R. Now, do not add 5 plus 3 plus 4 and say that's 7. Okay? You don't add the linear lengths. You are physically going to take your ruler and you're going to measure the length of this vector. Okay? That's going to be the result. You are going to measure from here out to here. And then you're going to take your protractor and you're going to measure this angle. Now, roughly, what's that angle going to be? Somebody throw out a number. Okay, 65 degrees. Okay, 70, something like that. But clearly, it's going to be between what and what? Between 0 and 90. Okay, just a ballpark estimate. This thing is going to be between 0 and 90. So if I don't have that angle, I've done something wrong. Now, the other one that tends to get screwed up is number 4, where you're going to add vector B and vector D. So again, all that I'm going to do is I'm going to make a sketch. Here's my system. I'm going to draw a vector B coming up like this. Now, D gets a little bit weird because D is like at 250. So you've got to measure around here all the way, and then you're going to draw vector D down here like this. Right? So, and again, this is just making a sketch of this. I'm going to get a ballpark idea of where this thing's going to end up. So when I draw that resultant from this origin out. Now, just based upon this simple sketch, Elijah, when I give this angle, between what two values does this angle have to be?
Between 180 and 270.
Perfect. Okay? Just based upon this sketch, I know that my angle, when I draw vector B and add vector D, has to be somewhere between 180 and 270. Don't give me this angle in here. It has to be measured around from that positive x-axis. So just as a sketch, this is where I'm going to end up. Got it? Good? Fantastic. Now, when you get to number 11, okay? So when you get to number 11, clearly you want to set up a scale, okay? Don't try and draw this thing 3.8 kilometers long. That would basically be like 2 miles. I really don't think you want to draw out something that's 2 miles long. So, on number 11, here's the basic idea of what's going to happen. So he's going to walk 45, then at 270, 225. So what you're going to end up with is, on number 11, and again, this is just like a rough sketch. You're going to start here. He's going to come 45, and then 270, and then something down here like this, okay? Just as a sketch, okay? Now, here's the deal. I think you end up over here somewhere, because I think it's like something like this. So, again, when you make this sketch, when you're going to give the angle, and this is going to be the difference when you look at number 11. So, if you're the search party, you're going to head out from here out to this point, okay? So if you have to give the direction for the search party, because that vector is pointing from the origin out to here, that angle has to be measured around from that initial positive x-axis. Now, but if you're Bob, and if you're Bob headed back here, Bob's vector is going to be measured from this point up to here, which means because his vector is going to be pointing up this way. So if you're the search party, you're measuring your angle from this x-axis pointing down this way. If you're Bob and headed back this way, you're measuring from this and coming up to here. So what do you notice about the length of the two vectors? They're the same, okay, otherwise known as magnitude. Okay? Beautiful, grand. Any questions? Make sure what I see beside like B plus D, whatever, what I want there is the value of the resultant. So many centimeters at so many degrees. What I'm going to then should be able to do is flip over and see, hey, here's, and clearly numbered. I am not going to try and search through and guess what is what. I should clearly be able to see, here's number 2, here's number 3, here's number 4. Okay? That everything is laid out nicely and easy to follow. We're grand. Now, like I said, do not hand that in yet. You will, you're just not going to hand it in today. So, here's how this week is going to play out. Today is Tuesday. So we're going to figure out how to use trig functions today and do all this. As you can see, it's a little bit simpler. And then on tomorrow, Wednesday, we'll review. Thursday is this test of velocity. So finish stuff up today, review tomorrow, test on Thursday. Life's grand. Okay, so shut that down while I hand out. All right, so what we're going to do next is figure out how to use trig identities. But I'm going to use what you've already done to transition into this next step. So, in case you haven't figured out, most vectors, when you add them together, aren't at this nice little 90-degree angle. In reality, most things are at like 75 or whatever angle there is. But the odd thing about trig identities, when you look at sine, cosine, tangent. Sine, cosine, tangent, those are the only ones we're going to use, are just sine, cosine, tangent. Those only work on what type of triangles? Right triangles. Okay? That's the only time sine, cosine, tangent work, is on right triangles. Most of what you're going to deal with aren't at right angles. So we've got to be able to make this transition. So what we're going to do is basically we're going to segue in between the two of them. So if you look at vector A, okay, so we're basically going to work this whole thing together. Okay? So you got vector A, which we said was 5 centimeters at 0 degrees. Now, don't draw this again. You already have this drawn. Okay? Don't draw it again. Now, so one way to get to the end of this point, okay? So let's say that David is here, right? So I can say, David, you need to walk 5 steps or 5 centimeters at 0 degrees. He goes, okay, I can do that, right? So he goes 0 degrees, it's along that positive x-axis. He walks 5 steps, hey, boom, he's there, life's grand. Now, there's another way that I could tell David to get to that exact same point. And that is like a coordinate system. So imagine this is, the room is laid out in one big x and y coordinate system. And I say, David, you need to walk out to the point 5 centimeters and 0 centimeters. And he'd say, hey, I can do that. So David's here and says, yeah, I can move out to that point. So if I tell him to move at 5 centimeters at 0 degrees, or if I tell him to walk out at 5 centimeters and end up at the point 5 centimeters 0, no matter what, he's going to end up at the exact same point. So we can either use an x and y coordinate system to tell him how to get to the end of that point, or we could use angles and magnitude and tell him how to get to that end of that point. Either way, he's going to end up at the same point. So, when you look at that sheet, so like I said, we're going to kind of do this together, and some of these are just going to make sense. You don't have to draw anything out. Some of these you will have to draw stuff out. So, on vector A, you have 5 centimeters at 0 degrees. So, what we're going to do is break these things down basically into their x and y components, which is basically saying, hey, what x and y coordinate system will get you to the end of that vector? So if you look at vector A, what's the x component of vector A? 5 centimeters. Positive or negative? Positive. What's the y component?
0.
0. So on that one where it says vector A, 5 centimeters at 0 degrees, don't miss this. You're going to put an x component of 5 centimeters and a y component of 0. There you go. Yeah, no, not of the 0 part. Now, if you look at vector B, which is 3 centimeters at 90 degrees. So what's the x component of vector B? Huh? Where do you have to move in the x direction? 0. Okay? It doesn't have anything in the x direction. Now, Ashley, what's the y component? 9. And so to get to the end of that point, how far would I move up? No, that's the angle I'd move at. How far would I move?
3 centimeters.
There you go, 3 centimeters. So for vector B, the x component is going to be 0, and the y component is going to be 3 centimeters. Good so far. Nothing too difficult. Now, on C and D, these you actually need to take your protractor and your ruler and draw it. Now I'm going to make a sketch of these, just don't do anything yet, don't do anything yet. You are going to need your protractor and ruler, so don't do anything yet. So I've got vector C, which is 4 centimeters at 120 degrees. So here's what you're going to do. You're going to come out here, and you're going to draw vector C, 4 centimeters at 100 degrees. And what you can do, bless you, is that you're going to measure, this is the first thing you're going to do is you're going to draw this vector. We're going to do 2 of these this way because you're going to see what's going to happen and then you don't need to do any more. So here's vector C. So what you're going to do is you're going to draw this, and then you are physically going to measure how far you move in the y direction and how far you move up in the x direction. So you're going to draw vector C, 4 centimeters at 120. You're going to measure this, and you're going to measure this. So this is technically called deconstructing a vector. Okay? Which if you want to make kids just completely glaze over, go, today class we're talking about deconstructing vectors. Okay? So basically, here's what you're trying to figure out. Is if David's here, I need to tell David how to get to the end of this point. So basically, we're reversing the process. Because yesterday I said, okay, if you take this vector and add that to the end and draw the resultant, that's what you all did yesterday. Today we're going to say, here's the resultant. What's another way to getting to that point? So another way to getting to that point is that you're going to measure this y component and you're going to measure this x component. Now, because it's in the second quadrant, Sydney, what sign is my y component going to end up being? Negative. What about my x component? Positive. So when you get done, you're going to have a negative y component, you're going to have a positive x component. Then you do the same thing with vector E. So, excuse me, with vector D. So for vector C and vector D, and you only have to do those 2. On the back side of this, on another sheet of paper, you're going to draw these vectors, you're going to measure the x components, and you're going to measure the y components. So, Garrett, stop that for a little bit. Okay, so as my class has pointed out, what pretty clearly what I had last. I had the X and Y switched. This isn't, we're not changing the system. X's are still here, Y's are still here. My bad. Okay, so what does somebody get for their X component when you drew it out of C? What did you get for that X component?
-2.
-2? Exactly? Okay, what about for the Y component?
3.5.
3.5? Everybody get something close to that? Okay. Danny, what'd you get for your X component of D?
-1.1.
-1.1. And for your Y component?
-5.8.
-5.8. Now, when you look at E, what's E's X component? -5. You don't have to draw that one out. And this is going to be 0. So, basically, if I just said, okay, let's pretend that you don't know anything about angles, positive, where angle is going to be measured, positive x-axis, 0, nothing. If I just gave you this set of data, you could draw every vector A, B, C, and D, and E. And you could draw them going, oh, well, that's easy. This I would go 0, I would go out to 5. This one I would go 0 and up 3. This one I would go over 2, up 3.5. This one I would go over 1.1, down 5.8, and then I draw the result. So this is just a different way of getting to the exact same point. Okay? Now, you can either do this graphically, or eventually here in about 10 minutes we'll go, oh, we have calculators that do trig functions. Oh, we'll just use those. Life will be simpler. Okay? Now, but this is important so that you say, okay, well, this is where these numbers are going to come from. Now, what you're going to do, and we're only going to do 2 of these, because literally, after 2 of these, you're going to see this process, and that's why we're only going to do 2 of these. But it's important that you understand the steps that we're going to go through. So what we're going to do down there on number 2, we're going to add together vector B and vector D. So here, and on the back side of that sheet that I just gave you, there's a set of steps that list out how you add these components together. Okay? So if you like steps, I just type that all out because if some people like steps, and that way I don't have to write it down, and you have that as a reference. So basically, here's the first step. As you break the vectors down into X and Y components. We already done step 1. Now, so basically step 1, you find the X and Y components. Step 2, you add them together. Okay? So, and like I said, the first time we're going to do this, we're going to do this graphically. Then, once you understand the graphic method, then the mathematics become much more simpler to look at. So, you're going to start with an X and Y coordinate system. You're going to start here. The first thing you deal with is the X components. So we're going to add vector B and vector D. So what's the X component? Let me cheese that up a little bit. So what's the X component of vector B? 0. What's the what's the X component of vector D? -2. Okay, so here's what you're going to do. You're going to start with this clean X and Y coordinate system. There's no X component of B, so we don't have to worry about that. So the only X component that you have is this -2. So what you're going to do is you're going to come out here from this X and you're going to measure out 2 centimeters. Okay? So this is the only X component that we have is right there. That's it. Nothing else. So this tells me how far I'm going to go in the X direction and in which direction I'm going to go. Now, what's B's Y component? 3. So now this is where we're going to follow the same pattern that we established on Friday. So from the end of this, I'm going to go up 3 centimeters because this is going to be B's Y component, which we said was 3 centimeters. So from the end of this, I'm going to go up 3 centimeters. Boom. Full stop. Now, from the end of B, what is D's y component? Negative 5.7, 5.6, whatever it is, okay? Right, now, so what that means is from the end of this, now I'm going to measure down in this direction, okay, just like you did from the end of this, I'm going to measure down 5.7 centimeters, whatever you measured for your y component of D. So, then, now we're at the stopping point. So we took the x component, we added this y component to it, and then we added this y component to it. Now, at this point, now it becomes just like what you did. Now, you're going to draw that resultant from the origin out to here, and now you're going to draw that resultant. But now, here's the beauty of this, and this is why now we can start to use trig functions once we get to this point. Eventually. Now, if you'll notice, what you have is this nice little right triangle. Now, eventually, then we can use, now we can use Pythagorean theorem. Oh, now we can use sine, cosine, tangent, all this stuff, because now I have a series of right triangles. So by breaking them down into their components, you end up with right triangles. Read.
So what about the fact that vector D, the y is supposed to be at 250 degrees? Do we just disregard that?
Yeah, because that right there, okay, by breaking it down into this, so yeah, D actually ends up down here like this, but what we're saying is that if you draw the x and then you draw the y at the back, you end up at the exact same point. So you end up at the same point, it's just that you're going over and down instead of just going straight like that. Okay? So, do this. Draw this x, go up 3, go down however many centimeters that is, draw the result, measure that, see how that compares to what you did on that first sheet when you drew vector B plus vector D going dink, dink, dink. Okay? Which is a highly technical term going dink, dink, dink. Oh, Garrett, shut her down for a second. Okay, so here's where we're at right now. So, and I actually drew this whole idea of A plus B plus C like 3 different ways. So, here's what you all did on the first assignment. You drew vector A, from the end of vector A, you drew vector B, from the end of vector B, you drew vector C, and then you drew the result. Okay, that's what you all did on the first assignment. Okay, and you were all happy and life was good. Ooh, got to use my protractor, we're cool. And you are. Now, so what we did next is we said, okay, if you take vector A, you can break vector A into its 2 components. Into a positive x component of 5 with no y component. Vector C, or vector B, has a y component, but no x component. And vector C has a positive y component and a negative x component. Okay? So that's what we established. So if you look at this, if you were to draw these out, and this is basically why you end up in the exact same thing. So here's vector A's x component. You went out this far. Now, C's x component brings you back in the opposite direction. So what you drew is that you drew vector A, here's this x, from the end of this you measured back here. So what this tells you is the net effect of the movement in the x direction. So this tells you, okay, this is as far out as I'm going to end up in the x component. Now, with the y component, that's a little bit easier, because both of your y components have the exact same sign. B has a y component that's positive, C has a y component that's positive. So what this tells you is how far up you go in the y direction. So you've got this y component and this y component. So what you end up with is this result. So in the greater scheme of things, and this is the big picture, okay, this is the ultimate big picture, is that what you end up with, as if you were to clear out all of the clutter, you end up with this nice little right triangle saying, in the net effect, here's how far I go in the x, This is how far I go up in the y component, and the net effect is I'm going from here up to here at that particular angle. That's the net effect of what you've got. And this is what you're ultimately after. So what you should see is that no matter how you add these vectors together, you end up at the exact same point. This is just a different way of getting there because you're only focusing on the x and y components. Got it? Good. Grand. Everybody's hip so far. Now y'all get to use your calculators. Get out your calculators. Woo! It's a good day. It's like, enough of this drawing stuff. I want to punch numbers into a calculator. Okay. Now, before we get too far, let me explain how the old style math used to be done. So, what you've got is we're going to do number 4, okay, and we're basically going to work this together. So, on number 4, you have 25 meters per second at 40 degrees. So let me make a simple sketch of what this is. Whoa. Okay. That's
Didn't like the calculators.
what it really didn't. Kind of flipped out.
Down arrow.
Okay, now we're back. All right. That was weird. Okay. So here's what you've got. Now, on number 4, I give you vectors A, B, C, D, and F. These are completely different vectors than what you've dealt with up above. Okay? So we're finished with that first sheet. So when I'm talking vectors A through F, this is a completely new set of vectors A through F. The other ones, we're done with them. Never speak of them again. Okay? Never speak of them again. They are dead to you. So I've got vector A, 25 meters per second at 40 degrees. So basically what we're saying is that we're going to launch a freshman at 25 meters per second at an angle of 40 degrees with the horizon. Okay? Now, what I want to know is I want to break this velocity vector up into the x component and the y component. Okay? Which I just screwed up again. Into the x component and the y component. Okay? So when this freshman is launched, I want to know what's going to happen here, what's going to happen here. Now, one option is that you can continue to use your protractor and your ruler, and you set up a scale and you draw the vector and you measure it, but there's a lot of uncertainty. Riley might get a completely different number, or very similar to what Courtney got, but because you're measuring, we're off by a little bit. Now, let me explain how, when I was going through school, how we did this particular calculation. Calculators, it took actually a while for calculators to be able to do trig functions. So, and this isn't my book, but this is a high school physics book from 1902. Okay? So this book is 112 years old. Now, and it's interesting if you go and you look at this, like if you look in the index, okay, in the back, there you cannot find 3 important words. You cannot find electron, proton, or neutron. At that time, we did not know that those particles existed. We didn't figure out the structure of the atom until like the early 1920s. So if you look at a physics book, even 100 years ago, the key components of protons, electrons, and neutrons, you could not find them. We had not discovered them yet. So in the history of science, the whole structure of the atom is pretty new. So even when I was going through school, this is what you had to do. In the back, in any math or science book, except for biology, because it's not a real science, it's true, you would find a table like this in the back. And so what this is a table of sine and tangent. Okay? And so what you would do is, like, if you wanted to use, like, let's say, for example, the sine of 40 degrees. You would go down here and you would look up 40 degrees. And it would give a mathematical value for the sine or the tangent of 40 degrees. then you would take the whatever number that you have and you would multiply it by this number. Okay, because your calculators would not do sine, cosine, tangent. They could multiply, okay, even when I was in high school, but they couldn't do trig functions yet because they hadn't figured out how to write the programs for it. So up until probably the mid-90s, if you went in the back of like chemistry, physics books, things like that, you would have this table of sine and tangent, and that's how you would get the numbers, and that's what you would plug into your calculators. Now, so when you look at this, quick review. We're going to work with three big ones: sine, cosine, tangent. Now, these are also on your big dog equation sheet. Okay, so if you're not sure what they are, those are listed on your big dog equation sheet. So sine is what? Opposite over hypotenuse. Okay? Thank you, geometry teacher, if you know this. Okay? Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And then the other one, big one we're going to need is the Pythagorean theorem, which is x squared plus y squared or a squared plus b squared equals basically your resultant squared. And this is functionally what we're going to deal with. Okay, so here's the first thing we're going to do. I got 25 meters per second. That's going to be my, which side of the triangle? Abby. Hypotenuse. Now, what do you know about the hypotenuse relative to the other two sides? It's the longest side. Your hypotenuse always has to be the longest side. Okay? Euclidean, non-Euclidean geometry, it doesn't make any difference. That's always going to be the longest side. So here's my question. Let's deal with the x, right? So, how can I figure out the x component of the velocity knowing this angle?
Use cosine.
Why?
Because you would do adjacent, which is x over 25 meters per second. Then you would enter your calculator as sine 40 times 25.
How about cosine 40?
Yeah.
Anyways. So, what Reed just said is that the cosine of that angle, and I'm going to put this just in generic terms, okay, just generic terms. So the cosine of the angle is going to equal my x component over my vector, okay, whatever this vector is. It could be velocity, it could be force, it could be displacement, it could be acceleration, okay? So my x component is always going to be the cosine of the angle times whatever that vector is. So this is how you will always find your x component. Now, don't sit there and memorize it. If you really want to memorize it, you can. But if you look at this and go, oh yeah, here's my angle, boom. This is why you always break this up into your x and y components this way, because it just makes it easy. Now, so in this case, what you're going to do, when you would plug into your calculator, is that you're going to take 25 times the cosine of 40. Now, what I would do, and even though we had calculators, my high school physics teacher, he was the same guy that taught me chemistry, would never let us use calculators on the test. Okay, you had to do everything by hand. So what I would do is I would come in here and I would find the cosine of 40 and get that numeric value. Then I would multiply that by 25 and I would get my answer. So I would have to look up the numeric value of the cosine of 40 degrees and then plug that in. And I'm guessing the cosine of 40 degrees is going to be like 0.766. I'm going to multiply that by 25, and what would you get?
19.15.
So we'll call it 19.2. Because I have three significant digits here, right? So I got to have three significant digits here. Everybody get this number?
No.
It's probably in radian.
I got negative.
Oh God, no, it can't be negative. Make sure you are not in radian mode.
That's a
Yeah.
degree. I did it both ways. I did it the prehistoric way.
The prehistoric way. Thanks, Riley.
The look is pretty ancient.
It is, yeah. So, okay. What do you, so, 19.2, yay or nay?
Yeah, sounds good.
We're good? Now, what units do I have? Mr. Baker?
That would be
That would be what?
in meters per second,
Why?
because that's what the vector is in, so.
Yeah, and I'm multiplying by the cosine of 40, which has no units, right? And I multiply that by meters per second, so I get meters per second. So what we're saying is that when the freshman is launched, the horizontal component of his velocity is 19.2 meters per second. Beautiful? We're grand. Now, Cindy, how am I going to get the y component?
You can do the sine of your angle times the vector.
Beautiful. So, to get my y component, because the sine of the angle is going to be my side opposite, which is my y, over whatever this vector is. True? So, to get this, I'm going to take this, just like what Reed did, I'm going to take the sine of the angle times my vector to get my y component. So, sine gets you y, cosine gets you x. All the time. Okay? Absolute golden rule. Sine always gets you the y, cosine always gets you the x. So, in this case, I'm going to take the sine of 40, and the sine of 40, the prehistoric way, as Riley puts it, is 0.643. So I would take 0.643 times 25. And what are you going to get?
16.1.
16.1 meters per second. Now, dare I say, let's think about this for just a second, okay, and see if this makes sense. So, what you all have told me is that my x component is 19.2 and my y component is 16.1. So I have an x component of 19.2 and I have a y component of 16.1. Does that make sense in terms of a 40-degree angle?
Yes,
Why, Paige?
because it's in between like 0 and 90,
Yes?
so it'll be in quadrant 1, which it'll be positive.
Yes? We're good so far. But mathematically, do these particular numbers in relation to each other make sense in terms of a 40-degree angle? Graber? That's what you get for shaking your head, yes.
Because the X is a little longer than the Y.
Yes? Why?
Because it's a 40-degree angle.
Okay, what if it was a 45-degree angle?
You can split it.
They'd be the same, right? Okay? And since my angle is a little bit less than 40, my y component is going to be a little bit,
Less.
and my x component is going to be.
A little larger.
Now, if it was 60 degrees,
The Y would be more.
the y would be bigger and my x would be smaller. Okay? So, just because your calculator, and I'll show you why this works, your calculator will lie to you. Okay? It's true. And you're going, no, it's my friend. No, your calculator will lie to you. Okay? Now, so what I want you to do then is go down and find me the components of vector D. Eventually you got to do all of these, but in the name of time I want to kind of shortcut this. So we've got vector A, we have the x and y component. So the x component is 19.2 meters per second, the y component is 16.1. Now, I want you to do the same thing with vector D. So to take that 11.4 meter per second vector, and if you look at, and if you make a sketch, you'll realize you don't need your calculator to do vector D. If you just make a sketch, you don't need a calculator. No, you can, but if you just, since it's at 270 degrees, if you realize where it's at, you don't need a calculator. Again, if you just think and step away from the calculator, because I promise you, Riley, no one is ever going to pay you $80,000 a year just to sit there all day and punch numbers into a calculator and find numbers. It's what you do with the numbers, that's what you get paid to do. So, really? No! Sheet. You're going to find the resultant of these two vectors acting together. You work these the same way every time. There is no magic shortcut. I promise you, I'm not going to walk in here tomorrow and go, oh, you know, all of those 5 or 6 steps that I told you to do yesterday, oh, we can just do this in one step. Okay? No. Okay? This is the most efficient, most reliable method of adding vectors together that are not at right angles. Okay? I promise you, I'm not going to come in tomorrow and say, oh, you don't have to worry about all that. Here's the easiest way to do this. Now, what I'm going to do is I'm going to show you a couple of different ways that you need to think this problem through. So, it's like this. What I did, because down below on number 5, what I want you to do is I want you to add vector A to vector D. So we're going to work number 5 together where it says A plus D. So I'm going to show you exactly how I want this done. Okay, exactly how I want this done. Now, so here's the setup. Okay? Basically, if you draw it this way, from like a free body diagram, all acting from the common center, here's the setup. Imagine that the freshman is being launched at a 25 meters per second velocity going this way. At the same time, there is a wind blowing at 270 degrees at 11.4 meters per second down like this. So what we're going to try and figure out is what's the net velocity of the freshman when we try and launch him this way into a crosswind blowing this. Okay? So we're going to try and figure out, okay, what is the net result of the velocity of the freshman? Now, sketched out like this, okay, this gives me some idea. If you want to think of this as like a soccer ball, somebody's kicking the soccer ball this way, somebody's kicking the soccer ball this way, I know that ball is going to go somewhere out here, right? Now, if you want to sketch this, and again, this is just a sketch. If you want to sketch this thing tip to tail, and that's a good idea to do, because then what you're going to get an idea of if your answer makes sense. So I'm going to take this 25 meters per second, okay? From the end of this, I'm going to come down 11.4, and then I'm going to draw that resultant. So what this does, okay, this gives me an idea of where I'm going to end up. Just based upon this sketch, I know I'm going to end up either in the first or the fourth quadrant, depending upon how this deal works out. I know I'm not going to end up in the second, and I know I'm not going to end up in the third. So what this tells me is that this angle is going to be maybe a little bit above 0 or a little bit less than 360, okay, as a ballpark. This is what this tells me. So if I end up with an angle of like 180 degrees, I've done something horribly wrong. Okay? It just gives me a sketch. That's all it does. All right. Now, here's the process that you're going to follow, and you can do. If you do this every time, you're going to be fine. Again, I am not doing this to be an ogre. Years of when I work problems and I've been doing this longer than you all have been alive. This is the exact process that I go through, because it eliminates stupid mistakes, and it forces you to think. So the first thing you're going to do is you're going to find the x and y components. You already have those. So in this case, we're going to add vector A to vector D. So on the back side, I'll show you exactly how this goes. This plays out. Make a chart. Here's your x. Here's your y. What's the x component of vector A? 19.2 meters per second. What's the y component? 16.1 meters per second. What's the x component of D? 0. Okay, so I don't have to worry about that one. A lot of times this is not going to be, this will be something other than 0. Now, what's the y component of d? Negative 11.7. It is vital that you have that negative sign on here. Absolutely vital. Because what you're going to do is that you're going to add these together. And this is what this sigma means. Sigma means sum. If you ever take calculus, you will see this a lot. Okay? I'm talking about the sum of these values. Now, check my math, but 19.2 plus 0 is still 19.2. You're going, wow, Mr. Burkham, you can do that in your head? Yes, I can. Now, I'm going to take 16.1 and add that to negative 11.7. What do I get? Danny, with the fuchsia calculator, what do I get?
4.4.
4.4? Everybody hip with this? We're good. 4.4? Beautiful. Now, when you get these numbers, here's the next step. You're going to make a simple sketch, and I emphasize just a simple sketch. Now, trust me, draw your x component first, then draw your y component. So now we're going to add these tip to tail. So I'm going to take this x component, and I'm going to go out 19.2 meters per second. From the end of this, I'm going to draw my y component, which is going to be 4.4. Now, this gets me two sides of my triangle. My resultant is going to represent which side? My hypotenuse. So what I don't know, I'm going to draw this a little bigger. So I need to find my resultant. That's going to be the net effect and the actual velocity of the freshman when we launch him into this crosswind. Okay? So how are you going to get that resultant?
Tangent.
No.
Pythagorean theorem.
You're a step. Pythagorean theorem, right? So you take 19.2 squared plus 4 squared, and then you're going to take the square root. It's like, so what'd you get? Come on, y'all are fantastic at doing this with calculators. Because it sucked doing it by hand. What'd you get? 19.7 meters per second. Now, is that the fact? Now, are you done? No, no. Because 19.7 just tells you the magnitude. What else do you need?
Direction.
You need the direction. Now, this is why it's a good idea to make this as a simple sketch. Okay? So, what I need is this angle. This is why you always draw the x component first, and then you draw the y component. So how are you going to figure out this angle? You know the opposite and you know the adjacent. Inverse tangent, right? Because you're trying to figure out which angle has that value, or that particular ratio. So you're going to take the inverse tangent of 4.4 over 19.2. Now, should this be a pretty big angle or a pretty small angle? Small angle. So what'd you get? Because in the old school way, you would divide 4.4 by 19.2, and you would get a number, and then you would reverse it, and you would go to this dative column, and you would find your tangent columns, and you would figure out which angle had that ratio when you divided it out. So what'd you get? What'd you get? 12.9?
Yep.
Okay? So this is going to be 19.7 meters per second at 12.9 degrees. Everybody hit. Now, this is where your calculator lies to you. Okay, you're going, oh no, yes. Now, I'm going to play the what-if game, and I'm going to pretend that this actually worked out to be negative 4.4. Okay? Now I'm going to make this negative. I want to make this negative 19.2. So, if we had ended up like this, at negative 19.2 and 4.4, if this is what had happened, okay, if this is what had happened, now, this is where your calculator lies, okay? If you try and find this angle, if you punch into your calculator, I want you to punch this into your calculator. If you punch into your calculator the inverse tangent of 4.4 divided by negative 19.2, tell me what you get. Negative 12.9. So your calculator tells you that that angle is negative 12.9 degrees. Can't do that, can you? You can't have a negative 12.9 degrees.
102.
Okay, so, but here's the bigger picture. You need this angle, right? So one option is that you would take negative 12.9 and add that to 180. Now, what I would do personally, this is me, old school. I wouldn't even worry about that negative. I would just take the inverse tangent of 4.4 over 19.2 and get 12.9 degrees. Okay, that's what your calculator's going to tell you the angle is 12.9. Then I would realize, oh, I'm just going to subtract that from 180 to get this angle. If it was down here, I would take that angle and add it to 180. So this is why you always want to work off this x component. And this is why you need to take the time and make a simple sketch, because your calculator will lie to you. All right, so by tomorrow, here's what I want. On number 4, you're going to finish, you're going to find all those x and y components of all those. Notice that in every number I've given you, you have 3 significant digits. Every one of those calculated x and y components should have 3 significant digits. So in number 5, you're going to add vector b to e and c plus f, and then you have number 6 and number 7. Those due tomorrow. All right, I'm done.